Okay, so let's unpack this. For what feels like forever, the cosmic forecast has been, well, pretty dramatic, hasn't it?
Absolutely. The standard picture, our home galaxy, the Milky Way.
On a collision course, straight for Andromeda.
Exactly. An inevitable crash, maybe about 5 billion years from now.
Leading to this giant mashup, right? Turning two spirals into one big elliptical blob.
That idea, yeah. Milkomeda. It's been etched into the popular understanding.
It's quite a spectacular, if slightly terrifying future.
And it was based on the best observations we had for quite a long time.
But here's where things get really interesting. New research.
Cutting edge stuff, yeah. Using incredible data.
From space telescopes, powerful simulation.
And it's suggesting that maybe that whole inevitable crash scenario isn't quite locked in.
Maybe not. So the universe's dance card isn't quite full yet.
It looks like the potential future for our galactic neighborhood is, well, much more varied. Less certain than just one big smash.
Okay. So our mission for this deep dive is to get into the sources, right?
Exactly. The research papers, the simulation details, the telescope data itself.
We want to understand why astronomers are shifting from inevitable collision to, well, maybe not, and what that actually means for us here in the Milky Way.
We'll trace that journey from the old certainty to this newer picture where even small things can make a huge difference over billions of years.
Let's start with that old story then, the Milkomeda prediction. What made everyone so sure a head-on crash was coming?
It mostly came down to measuring how fast Andromeda is moving towards us. It's called radial velocity.
How fast it's approaching directly.
Right. And we've known for ages, thanks partly to, early Hubble observations, that it's heading our way at about 100 kilometers per second.
Which sounds pretty fast on a cosmic scale.
It is. And if you just assume that's the main motion and you run the clock forward billions of years.
Yeah, a collision looks unavoidable, like two cars on a one-way street.
Pretty much. But the universe isn't a one-way street. Things can also move sideways.
Ah, the transverse motion. Sideways drift.
Exactly. And measuring that for Andromeda, its sideways movement relative to us has always been incredibly difficult.
But science moves on. Tools get better.
And that's where this new research comes in. A team from Helsinki, Durham, Toulouse, among others.
They weren't just looking at the old data. They had new tools.
Absolutely. They really leveraged the power of two huge space missions.
Okay. Who are the players?
Well, NASA's Hubble, still providing really precise measurements on that approach velocity, building on what we knew.
Still essential.
Yeah.
But the big news was Gaia.
Gaia, yes. ESA's Gaia mission. It's just, wow, it's like a cosmic map maker.
Measuring stars.
Billions of them, positions, motions with accuracy we've never had before.
So the team used Gaia data for what exactly?
They got these incredibly refined measurements of how stars are moving, not just in our galaxy, but in Andromeda too.
Both galaxies, that's key.
Crucial. It let them pinpoint the motion of the galaxy centers of mass much better, including that really tricky sideways component.
Okay, so they have this amazing, precise data, a real gold mine. What next? Simulations.
Yep. They fed this data, including the known uncertainties, because no measurement is perfect, right?
Right, always some margin of error.
They fed it all into these really sophisticated simulations, but they didn't just run one scenario.
No best guess simulation.
No, they used what's called a Monte Carlo approach. Meaning they ran 100,000 different simulations.
Wow, 100,000.
Each one started with slightly different initial conditions, position, velocity, mass, all falling within the error bars of the actual observations.
So exploring the whole range of possibilities allowed by the data.
Exactly. They traced all those possible futures out over the next 10 billion years.
And the headline. After running all those possible cosmic dances.
The big takeaway. That dramatic head-on collision within the next 5 billion years, the probability plummeted.
Plummeted to what?
Based on these simulations, only about a 2% chance.
2%? That's tiny compared to inevitable.
It's a massive shift in perspective.
So what caused such a fundamental change in the forecast? What were the old models missing?
This is maybe the most crucial part of the new work. A key factor that earlier models often didn't or couldn't fully account for.
Yes.
The gravitational pull of the Large Magellanic Cloud, the LMC.
Our little satellite galaxy. Really, it's big enough to affect this galactic collision course.
It is. I mean, it's not that small, maybe 15% of the Milky Way's mass. That's significant gravity.
Okay, fair enough. But how does its gravity change the Milky Way Andromeda picture?
Here's the clever bit. Its pull isn't just straight towards it. As the LMC orbits the Milky Way, its gravity exerts a tug on our galaxy.
Uh,
And crucially, part of that tug is sideways perpendicular to the line connecting us and Andromeda.
okay. So it's like the LMC is constantly giving the Milky Way a little nudge to the side as Andromeda approaches.
That's a great way to put it. A subtle, persistent sideways nudge, and over billions of years.
Even a small nudge adds up.
Exactly. In the delicate balance of cosmic gravity, it can be enough to turn what might have been a direct hit into a near miss, or at least delay the collision significantly.
So in many of those 100,000 simulations, the LMC's influence was enough to change the outcome.
In a large fraction of them, yes. Its gravity subtly altered the Milky Way's path just enough to avoid that early direct impact.
And how did they confirm the LMC was so important? Did they, run the simulations without it?
They did exactly that. They ran simulations deliberately excluding the LMC's gravitational effect.
And the result?
Those simulations tended to reproduce the older results, much higher probabilities for a direct, relatively near-future collision.
So it confirms it. The older models weren't necessarily wrong in their physics.
And it's incomplete. They didn't have the full picture of all the gravitational players, especially LMC, or the precision data to model it properly.
Okay, so if a direct hit within 5 billion years is only 2%, what happened in the other 98% of those simulations? Where did the possibilities lead?
They mostly fell into two other big categories, generally happening much further down the road.
Later outcomes. What's the biggest category?
The largest group, about 50% of the simulations, did show a merger eventually, but not for another 8 to 10 billion years.
8 to 10 billion. So much later than the original 5 billion year prediction.
Yeah.
How does that late merger work? Is it still a big crash?
Usually not a direct head-on smash on the first try. These scenarios typically involve at least one close encounter first.
Like a near miss?
Yeah, the galaxies pass relatively close enough for their gravity to really distort each other, pull out streams of stars, and crucially, sap orbital energy.
So they slow each other down with each pass.
Kind of like cosmic friction, yeah. They lose momentum relative to each other, making their orbits decay until they finally spiral in and merge. But that process takes time.
8 to 10 billion years worth of time, apparently. Okay, so that's 50% for a late merger after some close passes. What about the rest? The other, 48%?
That remaining chunk, roughly 48%, showed the galaxies basically continuing on their own paths for tens of billions of years.
So no merger at all in the foreseeable future.
In those scenarios, yes, they're the near-miss cases. They pass each other maybe at a fairly large distance, and their gravitational interaction just isn't strong enough to bind them together. They continue evolving separately.
Wow. This really paints a different picture for what our galaxy might look like deep into the future.
Completely different possibilities.
If we avoid a merger, or it's delayed way out to 8-10 billion years or more, the Milky Way could stay a spiral galaxy for much, much longer.
Exactly. It would still evolve, star formation would likely slow down, but it could keep that beautiful spiral structure.
But if a merger does happen eventually, then we
likely get the Milky outcome, a giant elliptical galaxy. The tidal forces during the merger are immense.
Ripping apart the spiral arms.
Yes, scrambling the stars, disrupting clusters, flinging some stars out entirely. It could also funnel gas towards the central supermassive black holes in both galaxies.
Fueling them up, leading to quasar activity or starbursts.
Potentially, yes. Triggering intense bursts of star formation before everything eventually settles down into a smoother, more featureless elliptical shape.
Okay, let's pull back from the galactic scale for a moment.
Yeah.
What does all this mean for us? For, our sun, our Earth? Does it matter to us if the crash is in 5 billion years or 10?
That's a really important point, and maybe a bit reassuring for you listening. While the galactic future is fascinating cosmic drama,
our local drama matters more.
Your fate, our planet's fate, is tied to a much more immediate clock, the life cycle of our own star, the sun.
Right. The sun isn't going to stay as it is forever. It's currently stable, burning hydrogen.
In its main sequence phase, but in about, roughly 5 billion years.
About the same timeline as the old collision prediction.
Exactly. Around that time, the sun will run out of hydrogen fuel in its core. It'll start to swell up, becoming a red giant. Eventually, it'll shed its outer layers and leave behind a white dwarf.
A hot, dense stellar corpse. And Earth's fate through that process is uncertain, but probably not great.
Likely not habitable long before the sun even becomes a white dwarf. The point is, By the time any Milky Way-Andromeda merger happens in these more probable later scenarios, 8 to 10 billion years from now,
Our solar system will already be fundamentally changed.
profoundly changed. Earth's destiny is far more directly tied to the sun's evolution into a red giant and white dwarf than it is to the exact timing of a galactic merger billions of years later.
So even if Andromeda misses us entirely, the night sky 5 or 6 billion years from now will look totally different anyway because of what the sun is doing.
Absolutely. The sun's transformation dominates our local future long before the galaxy potentially merges.
Okay, but let's go back to the simulations. If they're so advanced, using this amazing Gaia data, why are we still talking probabilities? 2%, 50%, 48%. Why not a definitive, this will happen?
It comes back to that measurement challenge we mentioned earlier.
The sideways motion.
Yeah.
Andromeda's transverse velocity.
Exactly. That's still the biggest source of uncertainty. We know how fast it's coming towards us very well. Gaia is helping pin down the sideways motion much better than before, but
But it's still not perfectly precise.
measuring that tiny apparent drift across the sky from millions of light years away is incredibly hard. And that small uncertainty in the sideways speed is what makes the biggest difference between a direct hit, a glancing blow, or a clear miss.
So more data is needed. This isn't the final chapter.
Definitely not. The researchers are very clear about that. This is ongoing science. Future data releases from Gaia are expected.
Promising even better measurements.
Even more precise measurements of star motions in Andromeda, which should help nail down that transverse velocity much more tightly.
And presumably we also need better data on the LMC itself, its mass, how its dark matter is distributed.
Yes, that too. Refining the details of the LMC's gravity will make the simulations of its effect on the Milky Way even more accurate.
So astronomers will basically rerun these kinds of simulations as the data improves.
That's the plan. As Dr. Telsawala, one of the researchers, put it, their work isn't about proving previous studies wrong, but about broadening the range of possibilities now that we can include factors like the LMC and properly account for the measurement uncertainties.
And others, like Professor Alice Deason, are suggesting maybe that whole Milkomeda narrative is just outdated now.
Yeah, she talks about maybe thinking of it more like a series of graceful near misses, a cosmic pas de deux, a dance rather than just a crash.
I like that. Pas de deux sounds much nicer.
And Professor Carlos Frank emphasized how amazing it is that we can now do this, use simulations to track billions of virtual particles under gravity and map out potential futures for entire galaxies based on real observational data.
It puts our own potential galactic future into a wider context, doesn't it? These mergers happen all the time across the universe.
They're fundamental. It's how large galaxies, especially giant ellipticals, are built over cosmic history. Mergers trigger bursts of star formation. They shape galactic structure.
So studying our own potential interaction helps us understand that whole cosmic evolutionary process.
Exactly. And testing how things like satellite galaxies affect the outcome, or how dark matter is distributed, helps refine the fundamental physics in our models.
What really strikes me is how sensitive it all seems to be.
How so?
Well, the idea that the gravitational pull of a companion galaxy, the LMC, which is only, 15% of our mass?
Right.
That its subtle tug could potentially redirect the entire future trajectory of these two massive galaxies, the Milky Way and Andromeda, over billions of years. It's mind-boggling.
It really highlights the interconnectedness and the long-term consequences of gravity in the cosmos. Small influences can change cosmic destinies on the grandest scales.
So picture is definitely shifting. Less predetermined crash, more complex dance.
A dance with multiple possible outcomes, yeah. Will our Milky Way stay a spiral? Will it eventually merge into Milkomeda far, far in the future? It depends crucially on those precise motions and the influence of companions like the LMC.
The universe, it seems, still holds some surprises. More data, better simulations will keep refining the story.
Okay, so let's sum up the key takeaway here. That long-standing idea. Milky Way crashing head-on into Andromeda in about 5 billion years.
It's looking much less likely now, maybe only a 2% chance, based on the latest work.
Right, thanks to amazing data, especially from Gaia, and simulations that now include the gravity of the Large Magellanic Cloud, the picture is much more diverse.
A merger might still happen, but probably much later, maybe 8 to 10 billion years from now, likely after some close passes.
Or there's a good chance, almost 50-50, that they might just miss each other significantly and continue evolving as separate galaxies for a very long time.
It really shows how dynamic this research is, how new observations are constantly updating our cosmic view.
And it makes you think, doesn't it? This question for you, the listener. How does this change your perspective? Knowing our galaxy might remain a spiral or merge much later after this complex dance, instead of just one inevitable crash, how does that frame our place in the universe for you?
You maybe consider this too. If the relatively small LMC can potentially change the fate of giants like the Milky Way and Andromeda, what other subtle things, maybe forces or objects we don't even fully understand yet, might be out there gently shaping the destiny of the cosmos on even larger scales? Something to ponder.